Hello, everyone. I think let's pick up one of the probably misunderstood topics, right? In linear regression. Linear regression, of course, is a very the most fundamental of all the machine learning algorithms out there, right? And let's look at what are the key assumptions of the linear regression. These are very important because the assumptions sort of are crucial, right, to be validated when it comes to any of the regressions that you would develop on. So when it comes to the linear regression model, these are the 5 assumptions. Let's dive into the details of each of these. So what does linearity mean? Right? Linearity, by definition, it means that a straight line, right? If you were to fit a curve between input and output, that is x and y, then you can fit a straight line, right, to explain the output for any value of, because in the straight line path of y is equal to mx plus c, you can substitute any value for x and get a value for y, right? So now, when it comes to multiple feature sets, and given a complex data set, there will be multiple such input variables, and hence, the straight line that we discussed simplistically, right? It becomes now a complex plane, right? And in this case, the epsilon essentially is the error term, right? So obviously, if the data that you see and find after the initial analysis, if it is non-linear, then obviously linear regression cannot be used for analyzing such models. So you will have to look at alternate regression models, right, to analyze the data. Now, obviously, it clearly, it's quite obvious that the curve on the right is a bad fit for when it comes to linear regression. Now, let's look at 2 topics which are sort of related, right? So let's take it up together. One is that all the residuals are expected to have a normal distribution. And the other topic is essentially homoscedasticity. And homoscedasticity, it essentially means that variance of error terms is constant, right? Or in other words, mathematically, if you were to represent this, the epsilon, the error term, that is essentially nothing but a normal distribution function, like a PDF, right? A probability distribution function with mu and variance, right? Now, if we look into how this would mean in a real life use case, obviously it's a XY plot, and you have a line that represents the predicted output variable, and the dots represent the observed output values. Obviously, you see values, the actual values lying on both the sides of the predicted variable, right? Corresponding that, you will see positive and negative error terms. Now, if you look at localized clusters, as we move from x is equal to 0 to x is equal to the maximum value, you see that these error terms in various ranges of x forms a normal distribution, right? And this is something that is, very much required assumption for the linear regression model. Now, looking at the second topic, right, which is homoscedasticity, the one that you see on the left side essentially means that the variance, right? The variance is constant as you span across the whole range of x. But in a heteroscedastic model, which is obviously not a good fit for linear regression, the variance, right, as you move along the axis, you will see that is actually increasing, or it could also reduce, right? So, and that's not a good fit for the linear regression. Obviously, the other key element, right, or assumption that one makes is multi-collinearity, right? And obviously, if you break down the term, you will understand this very clearly. What this means is multiple input variables essentially has a linear relationship with each other, right? What that means, let's look at this graph to understand what this means, right? Here are 2 independent variables, and the independent variable x1 and x2 are linearly related. Now, if we were to use x1 and x2 to explain y, the output variable, then there is obviously some redundancy, right? You don't need both the variables. You might as well capture the most relevant variable and use that to describe the output, right? So that is an optimization that you need to do as we develop the linear regression model, especially if you see high multicollinearity. When it comes to autocorrelation, I've again taken the stock market data, right? I mean, over I think a span of a year, that's example I wanted to use to explain this term, right? What does autocorrelation means, right? It means that the observations of all the error terms, right, are totally independent of each other, right? Now, if you look at the stock market data, especially at a certain window, it could be probably a day's trading window, it could be maybe a week. You see there is a pattern, right, of the stock prices. Maybe it is steadily increasing, maybe it is steadily decreasing, right? It's quite possible that situation happens. So in that specific window, if you look at it, the output, output is not totally independent of the previous day's stock value, right? Which means when I say output is not dependent, the error term of error n is not very different from error n plus 1 or error n minus 1, right? So when there is such a relation between the errors, obviously that's not a good fit for the linear regression model. Obviously, this autocorrelation analysis need to be done across the data set. This is a sort of a corner case which was highlighted just to show some patterns, right, on the data. Now, some of the quick fixes that you could do, right, when you see that the linear regression assumptions have been invalidated, like maybe feature engineering, transformation of data. You could replace inundate data where there are missing values with mean or mode, depending on whether it is continuous or categorical variables. You could also look at other regression models, like maybe a random forest, for instance, to see if you find that this particular data set is not within the boundaries of the linear regression model. Multicollinearity, especially, right, which could be reflected with the variant index inflation, various variance inflation factor that could be used to eliminate certain variables, right? Likewise, even error terms. There is a relation that points to the presence of autocorrelation. So you might probably want to look at time series or some other models, right? And again, what we are trying to do, although we showed the straight line dependence between output and input, it's actually a planar dependence, right? I mean, and there are error terms depending on the number of features which are out there. And obviously, there are tests that you need to perform specific to the data set, specific to the assumption which has been invalidated, right? And remedies also differ depending on if multiple assumptions are invalidated, etc. So there is no one fits all solution here. We discussed, I think, few of those cases, but then if there are use cases or situations which are specific to your data set, I think we need to dwell deep and decide what is best for your use case and for your model. Thanks for tuning in. Bye.